This is the Part 2 video of Lesson 2-9 for Secondary 1 Math, Writing and Interpreting Exponential Equations. Number 10. A pendulum loses 8% of its height every swing. If the height of the pendulum is 7.9 inches after 5 swings, what was the initial height of the pendulum? Round to the nearest whole inch. So we want to write an equation. Notice that the pendulum loses 8% of its height with every swing. We also know the height of the pendulum is 7.9 inches after 5 swings. So we got some key things. 5 swings, 7.9 inches, 8%, and it's losing it, right? That 8%. So we know we're going to be dealing with an exponential decay equation. So our equation is in the form y equals a times 1 minus r raised to the xth power. And we just got to identify these pieces. So the first thing is our initial value. Do we know what the initial value is? Well, we don't. In fact, it's asking us for the initial height. So we're going to put in a. Well, that didn't really help us much. But let's go ahead and see what else we can find out. We have 1 minus r. Remember, r is our percentage that it's losing as a decimal. So we're going to put in 0.08. And then x, well, we have that. That's the time. That's 5 swings. So we're going to put an exponent of 5. And we know after those 5 swings that the value or the height of the pendulum is 7.9 inches. So we can put that in for y in our equation. And now we can solve this equation. Now that we have it all set up, we're going to draw our line down from our equal sign, and we're going to divide by 1 minus 0.08 to the 5th power, or we could write it as 0.92 to the 5th power. And we're going to do that on both sides, because that's how we keep it equal. It's doing the same thing to both sides of our equation. And this will simplify to a being equal to about 11.98. Now, it did ask us to round to the nearest whole inch, so our solution to this is that a is equal to 12, or we could say 12 inches. So I've boxed our equation, and I've boxed the solution. Number 11. Vaughn's savings bond earns 3.5% in interest per year. The current value of his bond is $536.03 after 10 years. How much was the bond worth originally? So again, the question is, how much was the bond worth originally, or what's the initial value? So let's identify our important information. We know that it earns 3.5% in interest per year. We know the current value of this bond is $536.03, and that's after 10 years. So here's x. We know that this is our y, which is the value now, okay, our current value. And the 3.5% can be written as a decimal, which it would be 0.035. And this is r. So since the bond is earning, that's going to be increasing. So we're going to have exponential growth with a percentage. And the exponential growth form is y equals a times 1 plus r to the xth power. And so just substituting in these values, we would get $536.03 is equal to a times 1.035. So I'm just adding those two numbers, r and 1, and raising it to the 10th power. To solve, we can go ahead and divide by 1.035 raised to the 10th power on both sides so that we stay equal. And we'll find the value of a, which is 380 0.00, and the decimal continues, but so our solution is $380. So again, we have our solution and we have our equation. Now there is a different way of approaching this. Now thinking about this, if we switch and may say the current value and we put that in for A, so the $536.03 is A, then we could multiply by 1.035 still, but now we're going back in time to find the initial value, so we're going back in time 10 years. So we could set this up as y is equal to 536.03 times 1.035 raised to the negative 10th power. And if you put this into your calculator, it actually does result in our solution. So go ahead and put it in and make sure you can see that this works. And it's your preference on which way you want to do it. So we'll go ahead and set them both up for number 12 as well. Number 12. The half-life of a radioactive substance is the time it takes for half of the substance to decay. A form of beryllium has a half-life of 1 minute. After 6 minutes, a chemist has 0.1875 grams. How many grams of beryllium did the chemist start with? To write our equation, we might notice that there are no percents, and so our form that we're going to be using is the general form of exponential equations, which is y equals a times b to the xth power. Now looking through here, half-life, so that means that our growth factor or decay factor is 1/2, and it's going to be a decay factor because it's getting less and less. And then we know that 6 minutes have elapsed, so there's our x. We know that there's 0.1875 grams now or after the 6 minutes, so this is going to be y. Now we can substitute in what we know and solve for what we don't know. So we have 0.1875 is equal to a times 1/2 raised to the 6th power. So we're going to go ahead and we're going to divide by the 1/2 raised to the 6th power on both sides of our equation. And that gives us that A is equal to 12. So that means that it would be 12 grams. So we use G to represent that. So our equation and our solution. Now remember, there is that other way. So we could have substituted in nothing for y, put in 0.1875 for our initial value, and work backwards. So we're going to multiply this by 1/2 to the negative 6th power. So going back in time. So this is another possibility if you would prefer to do it this way. This is like going back in time, so we have the negative value, and the current value would be our initial value. Number 13. A mice population triples every month. After 7 months, there are 17,496 mice. How many mice were in the initial population? So again, finding our information, we know the population triples, so that's going to be our B. Tripling will be 3. And we notice that after 7 months, so this is going to be our X, and there are 17,496 mice, so this could be Y. And then we're going to substitute in these values to our general form since we don't have any percents. And remember, our general form is y equals a times b to the xth power. So substituting these values in, we get the equation 17,496 equals a times 3 to the 7th power. And to solve this, we're just going to divide by 3 to the 7th power on both sides of our equation. So we end up with a being equal to 8. So our solution, there were 8 mice in the initial population. Again, we could set up the other equation for this one. And if we did, we are just going to take our current value, this 17,496, and place it in where the A is, and then change the sign of our X. So we're going to have Y is equal to, so there's the or, Y can be equal to 17,496 times 3 to the negative 7th power. And we would get 8 mice. So one of those two equations, and then our solution. Number 14. The area of a sinkhole is increasing by 15% every year. After 4 years, the area of the sinkhole is 17.49 feet squared. What was the area of the sinkhole when it appeared? So we're going to identify the things we know. We know it was after 4 years, so there's our X. We know that it's increasing 15% per year, so it's a percentage, so we're going to change that to a decimal, and that will be R. So R is 0.15. And the area of the sinkhole is this now, so this is going to be Y, so 17.49 is Y. And we want to know the area of the sinkhole when it appeared, so this is our A, or our initial value. That's what we're looking for. Notice the percentage, and we know that it's increasing, so this is growth. So we're going to be using the exponential growth form, which is Y equals A times 1 plus R to the xth power. So substituting these values in, we have the equation 17.49 is equal to A times 1.15 raised to the 4th power. So to solve, we're going to go ahead and draw our line down and divide both sides by 1.15 to the 4th power. When we divide by this, we end up with A being equal to 9.99996, and so on. It continues here, okay? So to write our solution, we're going to run to the nearest whole. So we're going to say it is 10 feet squared initially. So our solution, our equation. And remember, we could write this in a different form and solve it differently. So our other possibility for our equation would be saying that Y is equal to 17.49 times 1.15 raised to the negative 4th power. So remember, we changed the sign, so we're going back in time, and we're causing now to be our initial, so we can figure out the past. Number 15. A medication kills a type of bacteria at a rate of 18% per day. If after 14 days there are 149.14379 grams of bacteria left, how many grams were there before the medication? Notice we have a percentage here. It's killing a type of bacteria at a rate of 18% per day. So that means we're decreasing at a rate of 18%, and that 18% is going to be our R, which written as a decimal is 0.18. Now it says after 14 days, so there's X, and then we have the amount after that, so this is going to be our Y. So to set up our equation, notice we have a percentage and we're decreasing, so we're going to be using the exponential decay form, which is Y equals A times 1 minus R to the xth power. So we're going to have 149.14379 equals A times 1 minus 0.18 raised to the 14th power. Then we're going to go ahead and solve the equation. And we're doing the same thing each time. We're dividing here by 1 minus 0.18 to the 14th power on both sides of our equation. And we find that A is equal to 2,400, which means there are 2,400 grams of bacteria before the medication started to kill it off. So there's our solution, and in green here's our equation. Now remember, we could simplify this. We could have simplified in here to say that it was 0.82. And we could also write this as a different equation. Remember, if we're saying we're going to go back in time, we could say that y, what we're looking for, is equal to the 149.14379 times the 0.82 and raise that negative 14th power. This concludes the Part 2 video of Lesson 2-9 for Secondary 1 Math, Writing and Interpreting Exponential Equations.